morning. Well, good morning to me and very good morning to Bob. It's very early morning in Houston, Texas today. For me, it's a decent hour. It's about 11 o'clock in the morning. Well, wherever you guys are, have a good morning or good afternoon or good evening. Welcome to our Zener versus Isolated webinar. This is the third time we run this webinar. We'll try to do our best to do you good service. We have collected several questions. You can start the presentation, Bob. We have collected several questions during the registration. We have some questions from previous webinar also that were interesting and we kept into this webinar. So let me do the few things we have to do here. Request some more control. Okay, Bob.
Got it.
Got it. Okay, so let's see if it starts. I got control, not yet. Says I can control it, Bob, but it seems like I cannot do it. Okay. So before we start, let me take a few moments to introduce Bob, my guest and my speaker today. We'll run the presentation. Bob has over 30 years of experience in the X world and is a CompEX instructor and an instructor for the ICEX CompEC scheme. He's also a member of the US ULSTP committee. And some of you guys already know him, but he's very, and you will, for those who are for the first time participating, you will see how well qualified Bob is today to run this webinar. Again, for everybody who's new and it's a must for us, we have to run a few minutes about GMI, who we are, what we do, and why we do it. So let me run this company presentation for 2-3 minutes, and then we go into our webinar. Okay, so GMI is an international company designing, engineering, and manufacturing intrinsically safe and seal certified devices, interfaces, which we use in automation packages from DCS to SCADA system in all the industrial sector, from oil and gas to petrochemical, food and bev. We have over 40 years of experience, and we are very proud to manufacture our product, design, engineer, and manufacture our product here in Italy, in our headquarters, in our own facilities. However, we are a global player with presence around the globe. Because we design IS and seal related product, we are we take special care in manufacturing our product because they are safety products. They are designed to make our world better. So we use state-of-the-art technology. We use a complete product traceability. So some of you guys might be our customer. One day, after 5 years, 10 years, give us the serial number. We will know everything about there is to know about that components, or that module, where the components came from, who tested them, what test result we obtained. So we try to, to have very high quality product. At the same time, we are SC Systematic Capability 3, so we are SEAL 3 certified, not only our product, but also our company and process. These are the products we manufacture, from I S Barrier to safety relays, isolators, also SEAL certified, power supply as well, SEAL 3 certified, multiplexers, termination board, custom termination board to interface with most systems in the market, hard multiplexers. We have a line of SPD or surge protection device. We have some loop indicators, and we run a division that does services and training in functional safety as well as EX in collaboration with Bob. As soon as this COVID get over us, we should be able to start going back to this live training and live seminar and courses. Okay, what's happening? Let's go to the next slide. Here we go. As we said, we are a global company. We have a direct presence around the globe in about 8 subsidiaries. We just started not long ago, about less than a week, a new operation in Australia. So that's very new. Of course, we had to do everything, in this way. through Teams, but it's has started. We have 80 contributors, we have about 200 people, and we do many courses. As I said, we used to do many courses, now we do many webinars. With Bob, we were discussing this morning, maybe too many, right, Bob?
Not too many, just very early.
Very early, okay. And thousands of installations around the globe. These are our customers. We basically interface with all the system vendors from ABB to Yokogawa. We've done many projects around the globe with all the EPCs. We supply to many OEMs, many in the US, but also Norway, Singapore, Russia, Siemens, Kongsberg, Dresser, Cameron, many companies. And we are in the AVL of many, many end users, the oil and gas. Okay, so this was my bit on the company. Now let Bob talk and give us a presentation, and I will try to see if I can release my control. Give up remote control. Okay, you should be back in charge, Bob. Before we start, Bob, sorry, let me say, you can pose question in the question and answer box. There is a box there, you can pose a question. We will try to get to it as soon as possible. There is a question that says, I can hear any audio. We've seen this problem in the past. It's not to do with us. You guys have to look at your setting in your, in your computer. The audio works well because I hear Bob, Bob hears me. So with the audio for us works okay. So what can we do? Nothing else. Let's go on, Bob. If you have any questions, just use the question and answer box. We will try to get to it. Okay.
Thank you, Paulo. And thank you very much, everybody, for joining us. And Paulo, you can hear me fine, no problems?
Yeah, you're doing great.
Okay.
I disappear, I'm just,
You're leaving me hanging. That's okay.
I just, when people look at you because you're talking, I want to be, on the background.
No worries. Well, no worries. Well, I want to echo what Paulo said. Thank you very much for participating. This is our, I think our fourth one, maybe our fifth one webinar that we've done. We've done some other webinars on different topics, including competency. We had one that seemed to be of interest, 6 common mistakes. We're going to repeat some of these and come up with some other webinars that we think are of interest. And if you have some suggestions, certainly in the chat, feel free to make some suggestions, because we're always looking for ideas to be able to present that to you. So feel free to let us know. We do have some questions that we will try to answer at the very end as well. So some of you have sent us some questions. We'll try to spend some time going through that. And we also have some polls that we'll kind of throw at you here as we go along. But let's get going. So hazardous areas. Let's see if I can move my screen here. There we go. So an explosive atmosphere. Again, this should all be basically repetitive for you all, but basically just as a kind of a primer here, hazardous area is a dangerous combination of flammable substances, oxygen, and sources of ignition. The flammable substances can be either gas, vapor, or dust. Oxygen is always present. The only way to avoid ignition is control the ignition sources caused by the electrical apparatus. The ignition sources that we commonly talk about, and they're referenced in various EN standards as well as IEC standards, as well as NFPA standards. They're things like hot surfaces, arcing and sparking devices, stray currents, exothermic reaction. All of these various things are ignition sources that we have to deal with. And when we're applying electrical equipment, instrumentation equipment into these hazardous areas, we have to take into account all of the potential ignition sources. So we have this combination of oxygen fuel and some sort of combustible material, and we get those in the right combination, then we can certainly have an explosion. So protection concepts, if you will. There's quite a few different protection concepts out there in the world, but the most common ones that we see that are typically used worldwide are concepts such as EXE, which is increased safety, EXD, which is flame proof. We do see a significant amount of EXP, which is purging and pressurizing. excuse me, and then of course EXI, which is intrinsic safety. So when we talk about these three concepts, the first one, segregation, encapsulation, oil immersion, pressurization, when we're talking about segregation, we're segregating one or more of those legs of the triangle from each other. So for example, if we pressurize an enclosure, we're removing the flammable mixture, the gas, the flammable gas or vapor from the source of ignition, right? That's a segregation. Flame-proof is where we contain it. We're assuming we're going to have all three legs of that triangle present. And when we have an arc or spark, it's okay because we're containing it within a flame-proof or what we might call explosion-proof type enclosure. Prevention. Prevention is basically increased safety and intrinsic safety. So prevention is basically saying, look, we're not going to have an arc or spark, or we're not going to have enough energy in this circuit that is going to potentially ignite the flammable gas air mixture. So increased safety, we do that by increased creepage and clearance requirements, making sure that there's no potential arcing. Intrinsic safety, we're limiting the amount of energy. So these are all the concepts that are commonly used. And again, these are just a handful of the most common ones. Other protection concepts are available as well. So focusing our attention on intrinsic safety, what are some of the components of what we talk about? It is one of the most flexible and cost-effective solutions. And the good thing is that if you're familiar with intrinsic safety installations, the concepts, if you will, intrinsic safety, for the most part, worldwide, the standards are all very, very, very similar, meaning that if you've done an intrinsically safe installation design and you've done it, say, for example, to comply with the ATEX directive, that the same requirements that are related in the EN standards are very, very similar to what you would find within the CEC in Canada or the NEC in the US or other world standards. Because we basically, intrinsically safe, it's a very worldwide, universally adopted and accepted protection concept. So basically, there's a term that we use in some of these terms, but if you see the slide below, you have what is called simple apparatus and intrinsically safe apparatus. We have cables. The associated apparatus is what we typically call our intrinsically safe barriers or barriers. So when you hear the term associated apparatus, that's another term for either an intrinsically safe barrier, or in some cases, people will call them isolators. And then finally, you have your control room, which is providing the signal out to the field. So what is intrinsic safety? Again, it's a prevention. The characteristics, it's a low power application. There's been many cases, and we've had some questions in the past where people say, hey, I'd really like to make, say, for example, a motor starter intrinsically safe or a light fitting intrinsically safe. And I've seen that in some specifications where actually clients are calling out, I want intrinsically safe lighting. Intrinsic safety is a low power, low energy type application. What we're trying to do here with intrinsic safety is make sure that any arcing or sparking that's taking place is below the minimum ignition energy of the flammable gases and vapors in which could be present. So we're typically talking about 1 watt of power or less. So it's generally limited to instrumentation circuits, very, very low power, 4 to 20 milliamp type circuits. So generally speaking, you really cannot do, say, a motor starter per se intrinsically safe. Lighting, for example, general purpose lighting or EX lighting is not intrinsically safe. However, instrumentation devices, signals, those types of devices, we certainly can make intrinsically safe. We have safety factors that are built in. There are requirements on isolation distances between IS and non-IS. And of course, we also need a barrier, and that's part of our system integrity. And again, the applications are instruments, measurement and control process, and some battery supplied devices. Now you'll hear this term a lot, intrinsic safety loop, or in some cases people will call this a descriptive system document or DSD, but intrinsic safety is a system concept, meaning that unlike some of the other EX protection concepts where they're more a standalone type protection concept, intrinsic safety is a system concept, meaning that it combines the apparatus at the end, the simple apparatus or the intrinsically safe apparatus, the cable, the associated apparatus, and our control circuit. So when we're doing intrinsic safety, we need to make sure that we understand and we need to match, if you will, our associated apparatus to the field device and making sure that our cables meet the requirements and that we've taken into account capacitance and inductance with regards to those cables. So we have to match it. It's a system concept. We develop an intrinsic safety loop. Now, there are basically two main types of associated apparatus that are out in the world. Zener barriers, we typically call these IS barriers. These are passive devices that use Zener diodes to divert the fault current to ground. Isolators, isolated barriers. We use this term, again, associated apparatus is what I would consider to be the official term, but we call really both of these intrinsically safe barriers. So sometimes people will call a Zener barrier an intrinsically safe barrier. They'll call an isolated barrier an intrinsically safe barrier. So just be aware of the terminology. But Zener barriers, we typically call our barriers. Isolated barriers are typically known as isolators. So the difference is that isolated barriers, they use safety isolation components, generally transformers or optocouplers to keep a fault energy to pass from a safe to a hazardous area. So Zener barriers are typically a passive device, fairly simple device. An isolated barrier uses a little bit more components, and we'll show that here in some of these additional slides. So this just kind of gives you a little bit of an understanding of maybe the cost benefits of using intrinsic safety versus maybe some of the other protection concepts. So if we look from a safety standpoint, explosion proof as kind of the benchmark, if you will, intrinsic safety is generally a more safe when it's properly used concept. One of the things that intrinsic safety is allowed to be used in is a zone 0 type environment if we have IA type barriers in our IA loop. Explosion proof or flame proof we cannot use in a zone 0 area. So there's a little bit more safety built into intrinsic safety. And there's more things that can go wrong with flame proof, if you will, or explosion proof, such as leaving bolts out, scratching the flanges, improper installation of glands. There's a little bit more there that can throw a monkey or throw something to make it not work. Certainly from a flexibility standpoint on intrinsic safety, there's an awful lot of options of which we can do. Installation cost on intrinsic safety versus, say, flame proof with cabling and glands, there can be some significant installation costs and maintenance cost savings, if you will. Now, again, these are somewhat generalities. Everybody's application is going to be different. But for example, typically if we're talking flame proof or explosion proof, the types of cables and types of cable glands, generally speaking, for power cables, we're going to use some sort of armored cable. We might have flexible conduit or rigid conduit. We typically are going to have, in some cases, barrier glands. With intrinsic safety, because that everything beyond the IS barrier is in effect safe, we can do things with, say, some of our cabling and some of the glanding that is not necessarily the same type of some of the installation details that we would do, say, for example, on a flame-proof installation. So again, it depends on the markets that you're at, depends on the standards of which you're following. So Paulo,
yeah,
I think we have a full question.
I haven't gone anywhere. Okay. So we have a pause, so some questions. So see that you guys have been following us. Huh? So let me see if I can launch the right poll. Yeah, okay, this is the right one. Last time we made a mistake, we launched the wrong poll. Okay, so it's a very basic question you guys should answer. What is the basic protection principle of IS? Of course, we're talking about barriers today, Zener versus isolators, so Bob gave us a very good introduction. And so, it's biased toward intrinsic safety, of course. But what Bob has been telling is very true, the cost of installation for IS barrier is less than that of an EXT enclosure. Although today, the wiring is still, prevalently the same because people follow a different standard. They want an armor cable anyhow, but it's not a safety requirement. Okay, let's see. We have some people are still voting. Let's give it a few more minutes. And the way I see it more safe is because we are preventing something to happen rather than trying to contain it. It's
Preventing versus containing.
Yeah, that's a big difference. As you said, you can make a mistake in containment, and you can't contain anymore. And even if it's working perfectly, to let an explosion happen, it just makes no sense to me. when there is no other way, you need to make a motor, 100 horsepower motor, diesel motor on a platform. You cannot make it intrinsically safe. You gotta find ways, but if it is possible. Okay, let's see how you guys been doing. Share the result here. Well, I guess most of you got it correct. I throw isolation there. A lot of you said isolation. It was a tricky one, it was a misleading answer. We use isolation in intrinsic safety, but it's actually preventing an accident, an explosion. Correct, Bob?
That's correct. That's correct.
So, okay, let's go next. Stop.
Okay.
Okay, I'll prepare for the next one. Okay, so you can continue, Bob.
Okay.
Okay, now we talk about IS
barrier. Okay, so what are the components, or how does a Zener barrier work, if you will? So if you can see my mouse on the screen, you have on your right-hand side, you have your input circuit, if you will. You have more or less three major components that are made up of a Zener barrier. You have a fuse, you have current limiting resistor, and you have voltage limiting Zener diodes. So if we have a fault condition, our Zener diodes, if you think of them, think of these as like maybe an overflow with a dam or something like that, where all of a sudden the water becomes too high, we have to allow that water to escape. So therefore, those Zener diodes, they open up. As the voltage increases, these Zener diodes open up and they allow that excess energy to go to a system ground. Now notice here, and this is the important thing to note on the right-hand side, with Zener diodes, it's imperative that we have a good, dedicated system ground that is separate from our normal ground. This is called our clean earth, as opposed to just our standard earth. Our requirements on our ground for our system earth for IS requires 1 ohm resistance or less. It's a very, very small amount. But basically, this is critical and important when we're using Zener diode type products. So if we have a fault condition, again, the Zener diodes open up. If, for example, the current becomes too high, the resistors kick on. If obviously we may blow a fuse. So if in fact we blow a fuse with regards to a Zener diode type product, we basically at that point we have to replace the Zener barrier, if you will.
Hey Bob, can I ask you a tricky question? We didn't plan this. I just want to ask you a tricky question. Why do we have 3 Zeners here and not 1?
Yeah. So what happens? So you actually, within the standards for fault tolerance for IA circuits. So if we're talking about, and we'll talk a little bit about this on the protection concepts or actually markings and all that, but all the protection concepts have to be able to withstand, have some sort of fault tolerance, if you will. And so for products that are suitable for zone 0 or an EPL-A, we actually have to have a double fault tolerant, if you will. So a Zener barrier or a Zener, we have to have redundancy in effect. So what you actually have, the difference, if you looked at this little chart here, just by looking at this, I can tell you that this is a schematic of a IA barrier, or a barrier that's suitable for protection into a zone 0, because we actually have redundancy built into it. So some people will ask the question, well, what's the difference between a barrier that's suitable for IA and a barrier that's suitable for IB? Well, it's basically the redundancy. That's what it is.
There is also another big difference, Bob, that sometimes this resistor, the current limiting resistor, is the only accepted method of protection for IA. You can only use a resistor to limit current. Whereas in IB, you can do with other active type of limitation, which allow you to have more power into IB. It is something that GMI has always avoided because you might not, if it's not certified for IA, and you use an IB in zone 0, you're not safe any longer. And we try to have the most stringent standard so that it fits in every application. But those are the difference. You're right. The amount of diodes, less numbers of diodes, and as a manufacturer, I can tell you one other thing. These diodes, 3 diodes, are tested individually before they are installed in the barrier. They're required to be tested.
So now an isolated barrier. Notice that we still have our fuse, we still have our current limiting resistor, we still have Zener diodes, but in this case, we actually have incorporated a safety transformer. So under this scenario, we have a fault condition coming in from, say, our control panel, but because it's isolated by the use of a safety transformer, that fault will not transmit over into the hazardous location on the left-hand side. So notice here, there is no need for a safety ground. So the use of an isolated barrier basically means, in effect, that we do not require the need or the use of a dedicated IS earth, which some of the questions that people have asked about, what's the big difference between an isolated barrier and a Zener barrier, that's the main difference. I mean, obviously there's difference in construction of the product itself, but the main thing from an application standpoint is the fact that on an isolated barrier, you're not required to have that dedicated, intrinsically safe, clean earth. And that's probably the biggest advantage for using an isolated barrier versus a Zener type barrier.
And also, Bob, I think, we're talking about safety earlier. In a way, it is a safer solution because when that safety ground is missing for whatever reason, or it goes above 1 ohm or disconnected, or, you are in a dangerous situation. With an isolated barrier, there's basically nothing you can do to render other than short, just put a jumper across it.
Right. So a Zener barrier under a fault condition, again, we potentially, if we had a fault condition, if we didn't have a good ground, or even if it somehow passes over to the normal earth, we have that fault in the hazardous location or whatever. The grounding issue is usually our biggest issue with regards to the use of Zener barriers. So that's why the good ground, the dedicated earth is so important. And again, the same thing happens in an isolated barrier. Again, we don't have to have that safety ground. Now, Zener barriers from a grounding standpoint, this is, sometimes people will ask the question, and I don't know if this was asked. We had this, I think, in the last seminar, but a lot of times people will actually utilize on your safety ground 2 conductors for your safety ground, for your IS earth. So you can see there's a safety ground connection here and a redundant safety ground, right? That is tied into, again, the safety system earthing ground, if you will. The reason why you might use two, it's not a requirement, but it's good engineering practice, is that when you actually have to go and periodically test to see whether or not you still have 1 ohm resistance or less on your cables, you don't want to do that testing while it's connected to your Zener barrier. You want to disconnect it at that point and then make your connections and then do your calculation or do your testing of it. If you do that while it's actually connected, or if you disconnect that safety ground during a normal process, then obviously you've at that point defeated the whole the whole need for the use of an IS barrier, or you've basically just defeated it right at that point. So a lot of people, which is good engineering practice, is actually use two redundant, if you will, two safety ground connection points for your intrinsically safe circuits. It's not mandated unless it's a client-specific specification. The standards don't require it. For the most part, I have yet to see a standard that says that you must use it, but it is a good engineering practice, and there are some stipulations that are spelled out in various world regulations.
Yeah, it's actually very good practice because you cannot test it otherwise. I mean, you can test it, but you need to, shut down or commit the air. You need to make sure there is no presence of gas in some area, in zone 0. How do you do that?
So again, this is just kind of showing a little bit in the same fashion. This slide shows a little bit of the same of what we already talked about. So we have a fault current potentially from a motor or something like that that comes back into the structural earth, that structural ground goes back into our Zener barrier and potentially creates a fault condition at that point. So that's, again, just another way of showing it that earthing and grounding of IS Zener barriers is an issue. It doesn't, and I don't want to discount the fact that Zener barriers are used worldwide and they're used safely, and people use them each day and every day. The important thing to remember with Zener barriers is just make sure that they're properly grounded, that you're following all the manufacturer's recommendations, and that you're following the regulations wherever you are in the world with regards to your safety grounds with regards to Zener barriers.
And Bob, you correctly mentioned they are safe, In fact, we have no record. I don't believe there is any record around the world of any accident caused by a barrier, whether it was a Zener barrier or an isolated barrier. Properly stored, properly used, they are 100% safe.
Right. So a little bit of pros and cons, if you will, and we've kind of talked about this, but your galvanically isolated barrier, again, no safety ground requirement, better overall accuracy. That lower installation cost, that has to deal specifically with the fact that you don't need a ground, right? And of course, it does allow the use of grounded or poorly isolated sensors. The Zener, you do have that dedicated safety ground, routine checks. The field sensor must be isolated. There is potentially some Zener leakage, if you will, from the accuracy. So that is a potential issue, but generally speaking, the main pros and cons, if you will, are spelled out there. Usually one of the questions people ask is that, well, from a pure, buying price standpoint, which is more expensive, which is less expensive? If you looked at it just from a single circuit, single channel type barrier, generally speaking, a Zener diode product will be less expensive than a galvanically isolated product. However, that being said, you're finding that many galvanically isolated products are becoming much more cost effective, and with some of the technologies to be able to combine as many as 8 channels in a single galvanically isolated product, you can actually find that a galvanically isolated product, actually from just a pure pricing standpoint, taking into effect nothing other than the cost of the barrier itself, can actually be more cost effective. So don't discount the fact that yes, you have more components on the inside of a galvanically isolated product, that you perceive that they're always going to be more expensive, but when you take into account obviously the wiring, all of the other things that need to be taken into account, you can find that galvanically isolated products can be a more cost-effective solution.
Yeah, also because the components that are in the barrier have, in the Zener barrier haven't changed in a long time, and they're getting more expensive. So anyhow, guys, you cannot get this wrong. I've answered a couple of questions live about grounding. I believe, now it's time to, okay, let's see. So the question is a dedicated and low resistance ground required in a galvanically isolated barrier IS installation? Read the question before you answer.
That's a tricky one there, Paulo.
We may try to make it funnier, otherwise it's too easy. Like when my daughter, she's been trying to take driver license. Nowadays they have 40 questions. And I try to help her out. I fail all the time. If I had to take a license today, I will not pass. A lot of these questions are misleading. They're just written in a way that you think the answer is that, and so I learned. Okay. Yeah. So in fact, the answer here, it is not required, right? Because the question was, is a dedicated ground required for a galvanically isolated barrier? Well, it is not required in a galvanically isolated barrier. It's only required on a Zener barrier. So let's see what you guys did. Well, most of you, 75%, got it right. So you've been following. Great.
Fantastic.
Fantastic.
All right. So let's continue on.
We'll get into it with the rest of because we have a lot of questions and answers that are all about grounding and installation and so on.
Yeah.
So we are in the closing of this presentation. Okay. So let's do like this. Bob, you can stop sharing, and I will share the answer we prepared for the question that were received during the registration process. So let me see if I can get the right presentation. Share. Okay. You see it, Bob?
I see it.
Great. So hopefully all of you guys are seeing it. So let's go to the first question. Okay. We just talked about this. IS isolator and Zener barrier. Is it just matter of grounding and cost? There were several questions about this. I tried to compile in one, and then they say pros and cons and what's better and when do I choose one and the other. So we tried to put together an answer that kind of summarized, but Bob already explained this very clearly earlier on, but basically the difference is the grounding and the isolation. And we talked about the isolation of the sensor, Bob, in the presentation. I don't remember.
I don't know if we really talked about it. When you say isolation of the sensor, you mean the
field device that the barrier is connected to. If it is a Zener barrier, it has to be 500 volt of isolation is required. You cannot ground, for example, take a thermocouple, ground a thermocouple, or you have to ensure that there is isolation in the field. You have grounding in the control room and isolation in the field. Whereas in a barrier, you don't need the grounding, and at the same time, you could have a grounded sensor. You don't have to worry about the grounded sensor. If a failure happens, I mentioned thermocouple because it was a natural instance, where in those leaf jacket of the thermocouple, they have a thin wire and there was vibration happening, and eventually the thermocouple itself grounded into the jacket, and the jacket is normally grounded.
Right.
So you end up with a grounded thermocouple, which creates other problem called Johnson compensation. You're misreading it, but it also introduces quite a dangerous situation for Zeners. So what else we mentioned here? Cost. You talked about cost. Let me reiterate that. Today, the difference is not that much. When you look at the SEAL 3 certified galvanically isolated analog loop barrier, well, yes, it will cost more than a Zener barrier. But if you look at multi-channel barrier, isolated barrier, we have up to 4-channel AI module. The cost is the same.
Let me add this too, if I could, Paulo. Historically, one of the advantages of Zener barriers was a very, very small footprint, meaning that they were very, very thin. And that was always, so your density of Zener barriers in a panel, you could shrink your panel down based upon the amount of Zener barriers. What you're actually finding, what you are finding, however, nowadays, as a matter of fact, GMI with their latest range of barriers, their galvanically isolated barriers, the latest generation, are much thinner. So they're actually taller, they're wider, but they're thinner, meaning that from a stacking density or density of being able to put a significant amount of barriers on a single piece of DIN rail, you now can do the same types of things with galvanically isolated products that previously, you were really taking up an awful lot of space. So that's one advantage that is now there.
With an isolated barrier, you can go as small as 6 mm, whereas in Zener barrier, they are not so small because internally the Zener diode required to operate are very big. For Zener barrier requirement, they're not the same Zener diode used in an isolated barrier because they have to withstand much bigger current and voltages. So they're physically, they're quite big. So the modular, I believe there are 17, 20 mm, Zener barrier. And also you need two, but most people don't realize that, or you need a double channel, or you need two barriers because you need one on one wire and one on the return wire, unless you want to ground the return wire.
Right.
That we haven't talked about much, but what else we mentioned here? We talked about, I think the rest is there. Maybe there's one big difference that we have not talked about. It's about the resilience of a barrier. And Zener barrier is designed for a fuse to open, and the fuse is spotted in resin. When you blow the fuse, you need to replace the product. It's very easy to blow the fuse. I mean, if your power supply fluctuates, above 25 volts, boom, you blow the barriers. If you have you short the wire, you do stuff like that, a Zener barrier will blow, and you need to replace it. An isolated barrier, it's a lot more resilient. You can short the wire. You have much bigger voltage fluctuation they can handle, and they typically will not fail as much as. So there is a cost in there also saving, maintenance and replacement cost. Okay, let's go to the next question. Well, we talked a little bit about this, Bob. Maybe you can give a little more explanation, difference between an entity concept versus a system certification.
Right, yeah.
I believe there are 2 or 3 slides for this. Okay, here we go. This is the first one.
Well, go ahead. Were you going to say something?
No, that you should talk about it. You are
okay. So basically, entity concept is more or less we're taking the details of all of the devices in our system, if you will. So, for example, if we take a transmitter or we take a intrinsically safe associated apparatus, a barrier, we're taking into account all of the parameters, the output parameters, the input parameters, all of that information for those individual devices, and that we're looking at them as a system. So we basically have to go through these types of checklists that you see on this slide. So is the barrier in compliance with the area classification? Cable parameters must match. Then we take a look at our simple devices. And our simple devices, by the way, they do not require certification. And more or less types of things that are simple devices are things like a thermocouple, a switch, a simple semiconductor. So non-energy storing type devices. However, we do require certification on IS apparatus, things like transmitters, proximities, those types of things. And again, the associated apparatus, they require the certification, which is our isolators and Zener barriers.
So at the end, I think we come to this, where both devices, the associated apparatus and the apparatus, have been given full certification, a set of parameters which you need to match.
That's correct. And so a lot of people get confused in this. It's not that difficult, but basically you just have to go through this and make sure that the parameters of your field device, your output parameters of your intrinsically safe apparatus, that they match up. So for example, if we look at that first line under the EX verification, you know, the output, if you will, is got to be less than the input voltage, in this case, of the device. So if our output is 30 volts and our input is 30 volts, fantastic. If our output is 32 volts, but our input max is 30 volts, then it's not okay. So we basically have to go through these types of steps to make those calculations, to validate and verify, to make sure that the device, not only from a, is it going to be able to pick up and do exactly what it needs to do from an electrical standpoint, but is it safe to be able to be used? So these are the calculations that we do. I'm sorry?
The cables also influence these parameters, right?
The what now?
Cabling, cables.
Cable takes into a very important part in this. When we had our seminar on the 6 common mistakes, that's one of the biggest things when I go out, and if I'm doing an inspection on EX intrinsic safety, I want to know the cable parameters, and I want to know the length of the cable, because cable will store energy. And so obviously the longer the length of cable, potentially the larger, well, there's going to be greater capacitance, right? There's going to be more energy storing the longer the length of cable. So for example, you might see an installation in which when we look at our loop drawing and it says we could only go 200 meters from our associated apparatus to the field device. Well, if I'm going in to do an inspection on that, I want to make sure that you haven't gone 210 meters or 250 meters. You have stayed within that parameter, because if we cut the cable or something happens at that point, then all of a sudden we've run into a situation where we've introduced more energy that will be above the minimum ignition energy amount that potentially could ignite the gas or vapor that's in that environment. So cable is a very important thing. It's very much overlooked, but it shouldn't be overlooked.
No, not at all. And, you know, you make it sound very difficult. You know, we need to check all this parameter, UO, UE, PO, CO, the cable parameter. But in reality, at least through GMI, and I'm sure there is other means around the world, but we provide for a safety loop verification tool online. You can download it online, you can work online, where the most difficult part is to collect the data, to have the information, to know what is the cable impedance and the cable resistance and capacitance. Once you have that, you can insert into a tool, and then the tool will do the work for you.
Yep.
All right, let's go to next. Is there any solution for this came just, I don't remember the name, but RS485. We do have a solution for RS485. This is more of a sales pitch, but just to introduce you, we have a solution where you can isolate and provide RS485 for input and output, or RS422. You can convert. Now, I'm sure you can do the same through a Zener Barrier, Bob, but I don't have experience with that.
I don't either.
Yeah, because the problem here is speed. You need to have a lot of speed. For example, we provide up to 1.5 megabit of speed. Otherwise, you cannot transfer the information. But there are solutions out there. Next, can you clarify isolation technique differences? This I investigate myself through our R&D team. And if you don't mind, Bob, I'll go through it. And then if you
please do.
if I'm doing something wrong, if I understood your question right, you know, there are basically 3 ways to isolate for IS purposes. You can use a transformer, so it's called a transformer isolation, or you can use an optocoupler, which is an optical device, like kind of 2 LEDs talking to each other. And there is another method that we have used sometime. I'm not sure if our competitor have used. It's called capacitance or capacitive isolation. Basically, you can see 3 pictures of these solutions. They provide means of isolation. The difference on a transformer is you can also transfer power, 24 volt. The other means can only transfer a signal, analog signal or digital signal, so very, very low voltage. For example, an optocoupler is basically in 2 LED that are flashing to each other, and they transfer only light. So you cannot transfer 24 volt. they have to be specifically designed, specifically certified to do the job. They're not standard components. There's not a normal transformer. It's not a normal isolator. There's a lot of rules to make it an intrinsically safe, so-called infallible components. But now in the question there, they were talking, the question was also about a relay. A relay, it's a mean of isolation, and a relay provides isolation. You might use relays for up to 2.5 kilovolt of isolation, but a relay cannot be used as a mean of isolation for IS purposes. Oh, was clear, Bob?
Clear.
All right. Little technical question. Let's go next. Okay, can you explain a requirement, or the requirement, imagine, for IS ground is for Zener and isolated barrier? Are there any differences in the wiring? There was also a question, Bob, which I came later. They talked about how do you do the grounding on a Zener barrier. So I also had a little picture there later. But why don't you go ahead? You know, the question is clear, right, Bob?
Yeah. So I think we've covered this to an extent, but basically just on the right-hand side, that's a picture of our isolated barrier or an isolator, if you will, galvanically isolated type product. Again, no need for a safety ground. The picture on your left-hand side is the Zener type, typically doing 2 grounds or 2 conductors to our safety ground. The only thing I would add to it is that generally in the IEC world, and it's reflected also in the EN standards, the minimum size, if we're using a single conductor for a IS circuit, must be 4 millimeter or greater. If we're using a redundant or 2 grounds, if you will, they can be 1.5 millimeter. So as far as the size.
And there's and I took a little picture here to show how to ground that. You know, one question was, how do I ground the Zener barrier? So
yeah, so if you see that one picture on the very top, actually that drawing, I don't know if you can see my mouse.
I didn't have a lot of room in the slide there.
No problems. You'll see the DIN rail there. Typically, the way you can identify a Zener barrier is you'll see some metal tabs typically, and so for convenience, a lot of times Zener barriers are actually just grounded right through the DIN rail, if you will, and then by putting an earth terminal grounded to the DIN rail itself, and then that's tied in. The key thing is to make sure that if we are using Zener barriers on the inside of a panel, and we're using it in mounting, say, our DIN rail to a steel plate, well, now all of a sudden we've now basically taken that safety ground all the way to dirty earth, if you will. So we want to make sure that we isolate, if we're mounting Zener barriers on, say, DIN rail, we use some sort of isolators to isolate that DIN rail from the dirty earth of a ground or of the panel itself. Now, there's different ways of doing it. That's not the only way. I mean, and obviously certain panels might have a phenolic backpan or something else as opposed to metallic backpan. But basically, we need to make sure that we take that into account.
There was a live question, Bob, which you can use this picture to answer. You know, they were asking if we can install the barrier on the same gear rail of other devices.
Yes, yeah, you can. Again, you have to make sure, however, I mean, if you want to mount other devices next to barriers, there is a segregation requirement of 50 mil between IS and non-IS circuits. So if you, say, had a DIN rail and you had some IS barriers and you wanted to mount some power terminal blocks or something like that next to it, well, you'd have to make sure that you maintain a separation between them of at least 2 inches. Now, there's some exceptions and there's things that you can use, such as partitions, but generally speaking, yes, you can. So you can mount different devices next to IS barriers. Just make sure that you keep in mind the separation between IS and non-IS.
In fact, I was trying to look, there was an example of some of these pictures, but now I don't see any example. They're typically, you know, kept separate with the blue cable tray. It's easier. But if you have space, you know, very small space you have to fit them in, you can, as long as you keep that 50 mil or 50 millimeters or 2 inches apart. Okay. Well, we already answered this question during the presentation. What about using Zener Barrier with a grounded sensor such as thermocouple? We said you cannot, because the fault current, if you have two ground connections, you have no means to control the fault current going to the hazardous location, right, Bob?
Correct.
And, we don't know what the impedance of this. This you have one over here. How many ohms you have there? Nobody knows. So the fault, the current will be diverted, will share among the two different impedances, if I understand this correctly. All right, let's go next. There was a live question here that I should have answered earlier. That says, how does an isolation barrier allow hard signal? Well, we looked at the transformer. The transformer has a secondary circuit in there to transfer arc. So there's a dedicated isolation circuit for arc that is capable of transferring I don't know how many kilohertz, 4 or 5 kilohertz, if I remember correctly.
I don't know.
The superimposed signal. You need to design a transformer to read it. Okay, so what about this question? Can I install a barrier in a classified area? Yes or not, Bob?
Yes.
Yeah. All right, let's go to it.
So what you will find, most barriers are actually certified to be installed in either a Class 1 Division 2 or a Zone 2 area. And more or less be installed in effect in a non-flameproof type enclosure. There are some specific details of it, but basically they are certified to be installed in a Zone 2 environment in and of itself. However, if you need to install them in a Zone 1 environment, then typically you would have to take that barrier and install it in, say, for example, an EXD enclosure or an EXP cabinet. So just be aware of that.
Yeah, there's a question. I'm going to go back to see if I can go back to one of the slides here, or maybe this slide here. Well, either way, there's a live question, Bob, that brings up an interesting point. It says, when we talk about grounding of Zener Barrier, does that mean grounding of barrier body or grounding of signals screened from the field? That's a good question, because screens have a special requirement for grounding in Zener Barrier.
Yeah. So it depends on the wiring regulations of where you are in the world, right? So typically, how are screens dealt with? The screen on an IS circuit typically are going to be separate from your safety earth. They're going to be grounded to your normal earth, generally, okay? So, but no, when we're talking about the actual grounding of the barrier itself, that's the housing itself, which is basically tying in the Zener diodes to the earth tab, which is in turn tied into the DIN rail, which is in turn tied into the grounding terminal, which is tied into a clean earth. But you also have to deal with the screens and drain wires and various other things, and where those need to be landed and terminated. So it is something that I would look closely at the wiring regulations within the country that you're in. But basically what we typically do, we do have to ground those as well.
If I remember correctly, Bob, it's important with screens you have to ground the screens, but you can only ground in one location. If you decide to ground the screen in the control room side, you cannot ground it in the field side, or vice versa, because otherwise
you create an antenna, and you don't want to do that. So you want to ground it. If generally speaking, if you have screens, what you would want to do is tie those into any unused terminal in the field. What's good engineering practice is tie them into an unused terminal. But a lot of countries will allow you to basically put a shrink tube over the end of the screen, crimp it, and allow it to float in the hazardous area. But then in the safe area, you want to tie it back, and you tie it back into a terminal or the earth in the control panel. So that's to address any inductive currents or any stray currents that could come into the screen, that you want to take those back into a safe situation.
All right, I hope we answered that question. So let's see another registration question. And again, guys, if you want to ask questions, just use the Q&A box. Well, we already answered this question, so let's move forward. This is definitely for you. What do all the symbol means in the EX marking? So we have a lot of markings. And you talked a little bit earlier about the marking. But
right. Well, I'll go through this real briefly. Just and it can be confusing. So what you see, the directive marking information on the left-hand side. So the CE is telling you that it's compliant to one or more European directives. Now, if you see a CE mark on a product and you don't see the EX in a hexagon, that means it's compliant to possibly another European directive, not necessarily the ATEX directive. So, for example, the pressure equipment directive or the low voltage directive or the EMC directive or what have you, they're all going to have CE marks, but they're not necessarily going to have that EX. So when you have a CE and the EX in a hexagon, that's telling you in effect that that product is compliant to the ATEX directive. The 0575, that's a number that's unique to every notified body. So whoever your notified body is going to have a 4-digit number. And it's going to be that same 4-digit number for that notified body, whatever product, whatever manufacturer that they'll go ahead and get involved in. Then we get into our equipment group, which basically reflects, in effect, anything surface industries. So anything above ground is going to be Roman numeral 2. Equipment category, in this case, could be 1, 2, or 3. And then we have G, which is for gas atmospheres. Then we get into our EX marking. So our EX is telling you it has some sort of explosion protection. IA in this case is intrinsic safety, suitable for zone 0. 2C is good for all gas groups. That's telling us that it's good for every gas group. 2C gases are acetylene and hydrogen. T4 is our temperature code associated with it. And then finally our IEC EX EPL GA, which is telling us basically the same information there that is told under the ATEX directive of 1G. So GA is telling us it's suitable for zone 0, zone 1, and zone 2 for gas applications.
Sometimes you find combination on the same certificate. You know, the device, translator, or a bearer might have several certifications combined, and the marking gets a little more complex than this.
Absolutely.
All right, we are into 1 hour. Let's see if you have a few more questions, and you guys want to stay with us, and then we go on to the closing. Well, we have a question about line monitoring. I'll try to make this very brief. When you're using an isolated barrier, you're basically isolated. So you put in a wall, a partition between your signal in the field and the control room. That has to go through the transformer. So the transformer, as we said earlier, allows to transfer it if you provide for a specific transformer to do that. You have to do the same for the line monitoring. So they are specifically designed, isolated barrier to handle line monitoring, whether it's DI or DO. And here are some examples. But basically, they depend on the type of IO card you're using, because some can bring information in one way, some in other ways, but they are available, these functions. I will skip this because we are running very late. There was a question about, can you give us a product description of your ranges? As I said, please, a brief description of our range for safety application. As we have a lot of barriers. Basically, you can use data for most applications. AI, AOs, and you see there's many DIs, DOs, temperatures, trip amplifiers, and special devices, vibrations to engage, power supplies, frequency, RS-485. There's many devices. I guess there was a question. There were a couple of questions that said, when do I select it in a bearing? When do I go for a bearing? When for an isolator? I believe we answered through this webinar, but let's see what we summarized there. I don't know if you saw the answer, Bob, or should I go through it?
No, I think we kind of addressed it. You know, one thing that just to highlight to make sure that everybody is aware of, GMI does not manufacture any Zener barriers. We
That was
don't.
also a question in the webinar. Do we manufacture? No, we do not.
Yeah, right.
Well, because
So
there is a market for it, honestly.
yeah, if it sounds as if we're anti-Zener barriers, we're trying not to be. It's just, it's a technology that's been around for a long, long period of time. It was the original technology for IS, but the marketplace in many cases is really looking for better products. And in my own personal opinion, I would use, a galvanically isolated product.
Sorry, I went the wrong way. Sorry. But yeah, we put three. I try to answer here. We give three questions. Why using it? So, well, an IS barrier is not available for sure. IS isolated barrier needs to be specifically designed for that type of loop or signal. Maybe, I don't know, AC signal, for example. You rarely find in barrier port, isolated barrier port. And when there is a resistant plant using Zener barrier, there's a lot of replacement. You already have a safety ground field. You might want to continue to use it. The space, constrained or physically do not allow room for isolated barrier. And there is one required transparency in that. So basically, it's Zener barrier. What they do not do is they do not interfere with the signal. So if you get millivolt, you will get millivolt. Instead of isolated barrier, typically you get millivolt, you get a milliamp hour. You can also have isolated barrier today, they have millivolt to millivolt or ohm to ohm. I think we're running late here. Somebody was talking about, there was a question about seal. I want to get more information about seal. I translated it into something like this. We have webinars on seal, we have webinar on functional safety, you can look it up. But, Bob, I believe a barrier being a safety device, somehow a seal, it's not a requirement for bystander, right, to have a seal certification for a barrier. No. But, it's not a bad idea. Correct?
Correct, yeah, and just the big thing that I would say, with regards to seal ratings, what it means in a nutshell is that the manufacturer in question has gone through a process to determine on every single component that is utilized in, say, for example, a galvanically isolated product that understands the failure rate of every single component. So therefore, when you talk about, we talked about a galvanically isolated product that has a resistor, that has Zener barriers, that has an optocoupler, that has all this stuff. In order to achieve and get a seal rating, you have to understand that every single component fails at some point in time. So therefore, in order to achieve seal, to get a high rating on it, you have to understand exactly how and where that's going to fail, and hopefully have a good understanding of at what point in time it will fail. So what that basically means for you as a consumer is that if a manufacturer does have a seal rating on this that's been validated and verified by an independent agency, that means that they've actually gone through that process and they know that this product will last a significant period of time under the circumstances in which it's supposed to be applied. So that's the big advantage of having something that's seal rated versus something that's not. It doesn't mean that it's safer. It doesn't necessarily mean that it's even a better product. But what it really does mean is that it does mean that from a longevity standpoint that that this is going to last a long time, basically.
It's more reliable.
It's more reliable, yes.
We are running 10 minutes into our timing. I don't know if I see that we have about still a good amount of people online. Let me see if you have a few more questions. This can be difficult to answer. Isolated barrier requires a power source. So does this increase my power supply need? I don't believe so 100%, but we try to put together this idea, where you have And Zener Barriers basically loop power, but you get a lot of voltage drop across the current limiting resistance. In the isolated barrier, it is bus power, so you get a more defined power output. So if we say you get 16 volt, you get 16 volt here. It really depends on the impedance of this resistance. In reality, a Zener barrier or an isolated barrier power requirement are basically the same. Because the power that is, you either provide the power through the power supply externally or through the power supply inside the barrier. But at the end, you need to provide the power transmitter, and for the length of the wires, for your analog output or analog input card. So the difference is very limited. There is some extra power consumption on the isolated barrier, but it's not that much. Trying to move faster because this one we cannot go through this time. It's too much. I would like to know fundamental factual safety. I would like to know about safety relays. Guys, you know, you always in every webinar we get questions like this about other webinars. Just go online, look them up, and you can see we have many, many webinars. You can try to find the one that suits you and go for it.
And don't forget, by the way, all of these webinars that we've had previously, and I think we've done all these at one point in time, it's all on YouTube. So you can just go to the GM International YouTube page, and you can view all of these webinars that we've done previously on YouTube. So, you know, obviously register for upcoming ones because we can try to answer your questions. But if you want to get some information, you don't have time or it doesn't work with your schedule, certainly go to YouTube and take a look at the webinars that we've already done.
Let's see how we did. Let me launch a poll here, guys. What do you think? We did okay or not? Because, you know, we take our time, effort. It's also very demanding being in front of this camera for an hour and 15 minutes. And I get exhausted at the end. Okay, well, it looks like most of you say we're doing great. That is good. Let me go here. Thank you. And boom. All right. Share the results so you can see how you guys saying. So thank you. Thank you for the response. Thank you for being with us today, this morning. Thank you, Bob. Thank you for getting up so early and, you know, so well presenting the information. Guys, look up for our, you know, following webinars. That's it.
That's it. Thank you very much.
Thank you. Ciao, Bob. Ciao, everybody. Thanks.
Ciao.
Bye-bye.